In this problem, we illustrate a couple of different ways to look at a moment calculation. And specifically, we've got a physical scenario where we've got a lug nut on an automobile wheel that we're trying to loosen. And the question is, how do we apply the force in such a way that gives us the best chance of developing enough of a moment that we can loosen the lug nut? And so the first part of the question says, according to the force as applied in the figure, in the vertical direction, can we loosen the lug nut? And the second part of the question says, if we can apply the force any way we want to at point A, how would we do it in such a way to maximize the moment and give us the best chance to loosen the lug nut? So this gives us a chance to again connect the physical scenario of what we're trying to do with the mathematics that we use to describe it. Since this is a moment calculation kind of a problem, we're going to use an R cross F kind of analysis. So let me go ahead and just write what our approach will be. So step one is we're going to write R and write F. And we're going to do that with respect to the coordinate system that is defined on the figure, which is X, Y, and Z, our usual right-handed coordinate system. You should note that the lug nut itself is on a bolt, and the bolt axis is coincident with the X-axis, and that's going to become an important part of the problem a little later on. Second thing we're going to do is we're going to calculate the moment, and that's going to enable us to make a decision. And the question there is, with the force applied as shown, can we loosen the lug nut? The third part of the problem is that we're going to find M max, the maximum moment that we can generate. And then we're going to make another decision. Is that maximum value of the moment enough to loosen the lug nut? Now what we know is that it takes 14 Newton meters around the x-axis to loosen the lug nut, and so that's the magic number that we're looking for throughout the analysis. Before we start, let's do a little trigonometry to set up the rest of the problem. What we need to do is find a way to express R and F. Part of the description of R is going to rely on this angle right here, which is made by the long arm of the wrench, and we're going to find this angle right here, this angle theta, and it is going to be easy to calculate using the two dimensions that are shown there, 0.3 and 0.5 meters. We can go ahead and write an equation which is something like theta equals to 36.9 degrees. So again, just basic trigonometry we're using there to set that up. We're going to use that angle to go ahead and write R. So in step one, let's do that. Let's write R and F. So R is going to be a little bit more difficult to write. Let's go ahead and see if we can do that. So let's see what we have to do here. So I'm going to do this in blue, and if we start at the origin where the nut is in contact with the bolt, in order to get out to where the force is applied at A, we've got to step out along the x-axis, 0.1 meters, and then we've got to step out on the y-axis, back here, in the negative direction, some distance that we'll have to figure out, and then we've got to go up the z-axis to get to point A. So the vector R now is going to be somehow like that. That's the one we're looking for. And so we can write that in a pretty straightforward way. That's just going to be 0.1 in the I direction minus the projection of the length of that wrench onto the y-axis. That turns out to be minus 0.5 times the cosine of 36.9 in the j direction, and then it's going to be, as given on the figure, plus 0.3 in the k direction, and that all has units of meters. When we do the math, this one turns out to be 0.4, and it's in the negative y direction. And then F is easy to define. We're told that it is vertical, so it is minus 30 K. It's got units of newtons. So for this first part of the problem, we know the direction of F, and we can just write it straight away. So that means for the second part of the problem here, we're going to be able to calculate the moment in a pretty convenient way. All right, so for step two, we're going to calculate the moment, and we are going to use that to make a decision. So M the moment around the origin is going to be r cross with F. This is going to be 0.1I minus 0.4J plus 0.3 in the K, and that's crossed with minus 30 in the K direction. This just turns out to be 3J plus 12I. That's going to have units of Newton meters. So there is our moment vector around the origin O. And the question is, how do we make sure that we understand what the moment is around the axis of the lug nut? Because that's what matters here. We have to make sure that we turn the nut around the axis of the bolt in order to loosen it. And so the way we're going to do that is we are just going to project that moment onto the axis of the bolt. All right, so in order to project onto the bolt axis, we're going to write something that looks like this. The moment around that x-axis is equal to the moment around the origin dotted with the I unit vector. And that's going to be equal to 12I plus 3J dotted with the I unit vector. So this just equals to 12 Newton meters. That is the torque we're generating around the bolt axis. So our decision is 12 is less than the 14 that is required. We cannot loosen the nut. Okay, so with the force being applied the way it's shown in the figure, we just cannot generate enough torque to do that. And the question is, if we orient the force in a different direction, can we actually generate enough to turn the nut? Let's find out. So step 3, we're going to find M max. So the way we're going to do this is we are going to maximize M by orienting F perpendicular to the wrench arm. Okay, so we're going to sort of write this in a scalar way. We would write M max is going to somehow be F times some moment arm D. That moment arm D is going to be the perpendicular distance from the axis of interest to the point of application of the force. Okay, now here, let me go back to the figure. Here we see that this distance right here is D. D is really equal to 0.5 meters. And so what that means is if we apply the force perpendicular to the arm of the wrench, that is going to give us the maximum. So let's go back here and do that. What we're going to find is that M max, and this is the max around the x-axis, that's just going to be equal to 30 newtons times 0.5 meters. That's equal to 15 Newton meters. So our decision here, 15 is greater than the 14 Newton meters that are required to turn it, so it is possible to turn the nut. Let's go back and review what we did. We have this typical physical scenario of trying to loosen a lug nut on an automobile wheel, and we've got a wrench that we can use to do that. And the question is, how do we orient the force on that wrench to give us the most torque around the bolt axis? So in the first scenario, we do it with the force in the direction shown in the figure. And when we do that, we can write an R cross F kind of equation to determine the moment. We project that moment onto the x-axis, and what we find out is that we cannot generate enough torque to turn the nut because we don't have the force oriented in the correct direction. If we orient the force in the right direction, that is perpendicular to the arm of the wrench, we can generate enough torque to loosen the nut. And in this case, we just get over the limit. We have 15 Newton meters generated. We only need 14 to turn the nut. So it is possible in this case to do it if we orient the force perpendicular to the arm of the wrench.